In the back of your eye sits photoreceptor cells called rods and cones. These cells of your retina contain a protein called opsin, which are directly responsible for starting the downstream signal that gets sent to your brain for sight through interacting with a photon. The direct part of the protein that can interact with a photon is the chromophore called 11-cis retinol. This chromophore is covalently attached to the protein and sits there, and when interacting with a photon, it causes photoisomerization. This causes a flip in the configuration between carbons 11 and 12 from cis to trans. This one change leads to a downstream electrochemical signal to be sent to your brain to help interpret what we see, all while other biochemical processes happen to flip the stereochemistry back for future interactions. But why are we talking about it? If we look at the molecule 11-cis retinol, we can notice one thing. It contains a lot of double bonds. One thing that we didn't learn about osmium tetroxide in our last video is about how toxic it is as a very strong oxidizer. We can almost begin to imagine the kind of damage this can do to a very important molecule that sits in our eye. Inhalation or even just exposure to the vapor can cause some serious damage. But throughout this video, we're going to talk about two methods that chemists have used to allow working with osmium tetroxide to be more manageable and less of a health risk. One of the first approaches is to use a catalyst that regenerates osmium tetroxide after reactions so that it can perform future reactions. This allows the use of small amounts of osmium tetroxide to be used for large-scale reactions, minimizing the risk by minimizing the amount of osmium tetroxide needed to be used at all. The second approach avoids using osmium tetroxide altogether and relies on potassium permanganate. The permanganate ion interacts with the double bond in almost an identical mechanism as osmium tetroxide, resulting in that syn-1 diol as before. So what's the catch here? Potassium permanganate is also a strong oxidizer, allowing us to form syn-1 diols. The catch here is if the reaction isn't kept basic and cold, it is prone to overoxidation, leading to unwanted products and unwanted side reactions, giving us two alternate methods, one that uses a catalyst and one that uses potassium permanganate.